Hello, my name is Paul Geyer, and I'm here to chat with you today about control and chemical feeding for wastewater treatment plants. This is what I'll be talking about today: related criteria, use of the criteria, policies, information required, and then the heart of the matter: wastewater treatment systems and chemical handling and feeding. And by way of introduction, this is just a little bit about me and what I've been doing for the last few decades. This discussion contains criteria on metering, instrumentation, controls, and chemical feeding devices used in wastewater disposal systems. Certain criteria related to the subject matter appears elsewhere, of course. These criteria indicate simple recommended practices applicable to plants with up to 5 million gallons per day average flow. Specific design problems may require departures from these practices, therefore use these criteria with discretion. For example, use of computers and microprocessors for data logging, indication, and process control is considered an emerging technology. This technology is presently primarily applicable to large wastewater treatment plants with adequately trained staff to maintain the hardware greater than 10 million gallons per day size. However, improvements in electronics, hardware, software, and sensing devices, primarily sensing elements, will make this technology more desirable for smaller plants. Detailed information is not included for such emerging technology because of its state of rapid change and because additional development and application experience needs to occur before application to the smaller facilities is justified. In the tables, certain abbreviations are used: E, O, and S, and they mean E is an essential item described and is required wherever particular applications occur. O is an optional item described which may be required contingent on specific plant needs, and S stands for special case items that are sometimes used in large installations or where process variable control is critical. Devices and systems should be as simple as possible. In any installation or facility, equipment procurement should be limited to the smallest practicable number of manufacturers. Provide elements to measure any function essential to proper operating control and evaluation of plant performance. Provide remote readouts only where operating convenience and cost savings outweigh added maintenance needs or where hazardous wastes are being treated. Record functions that significantly affect public health, the environment, or economy of operation. Consider data logging devices where costs can be offset by reduced operating manpower needs. Consider automatic controls where significant improvement in performance will result or where costs can be offset by reduced operating manpower needs or where treating hazardous wastes. Otherwise, keep controls as simple as possible. Wherever feasible, use fixed or manual controls, for example, weirs, launders, siphons, or throttling valves, in preference to mechanical devices. Use direct acting controls, for example, float valves, in preference to electrically or pneumatically actuated devices. Always consider the effects of possible control malfunctions. Standardize equipment wherever possible. Use identical or similar components to the maximum extent. Instrumentation, control, and feeding equipment should be homogeneous, that is, all self-powered, all pneumatic, and so forth. Equipment accuracy tolerances should be as low as possible and consistent with the functions desired. Before selecting equipment such as meters or feeders, compute the required maximum and minimum capacities and keep ranges as narrow as possible for any piece of equipment. New products and applications are constantly being developed. Obtain the following information to assist in equipment selection: the type of treatment, chemical, physical, and bacteriological qualities of raw wastewater, treated wastewater, and permissible discharge limits. Variations of flow rate for raw wastewater, ranges of other related variables, size of treatment plant, and effluent disposal conditions. With regard to the wastewater treatment systems and the primary measuring devices are required at critical locations in wastewater treatment systems to sense and measure flow, pressure, elevation, temperature, weight, and physical and chemical characteristics of process streams. For types of device, see Table 1. For examples of location of measuring devices and types of measurements for industrial waste treatment systems, see Table 2. Different types of measuring devices are available for each application. The listed capacity of a device includes most sizes and types of the device that are available. The range is the useful turn-down ratio of a particular device. Alarm functions and many control functions require only the presence or absence of a process variable input for their operation. For example, a sump pump may start if the liquid level is above a certain point, or a tank heater may start if the temperature is below a selected point. Control these functions by discrete devices such as flow switches, temperature switches, level switches, and pressure switches. If the actual status of the process variable is required rather than on-off for indication or control, an analog primary device should be used. Some alarm switches are not included in the tables. For example, clarifier torque switches, speed switches, and other equipment protection switches that are normally supplied with the equipment. Primary measuring devices for wastewater systems must meet more rigorous operational requirements than those for water supply systems. Selected devices constructed of materials impervious to the corrosive effects of the wastewater. Consider plugging of impulse or sampling lines and buildup of solids and grease on analytical probes when specifying these devices. Instrumentation covers all secondary instruments such as gauges, indicators, recorders, or totalizers needed for efficient operation of wastewater treatment systems. Information sensed by a primary device is translated by instruments into an operator-usable form called a readout. Most analog primary devices require secondary instruments, although a few, such as displacement meters, contain built-in counters. Instruments may be obtained in any combination of totalizing, indicating, or recording of information developed by primary devices. Other more sophisticated forms of instruments, such as summation and multiplication of variables, are possible, but are not normally needed. Select means of transmitting information from primary measuring devices to secondary instruments from the following. Mechanical. Transmission distance is limited to a few feet. Consider the effects of corrosion, wear, or icing on mechanical linkages. Pneumatic. Transmission distance can be up to 1,000 feet. Reaction time of pneumatic loops is relatively long if transmission distance is long. For electrical devices, there's no limitation on distance. Analog signals may require amplification for transmission distances greater than 1,000 feet. Remote indicators should provide the operator with the status of any function necessary for remote operation of the plant. Panel lights should indicate the on-off status of pumps or other discrete devices, alarm functions, and operator-actuated functions. For example, initiate backwash, fill day tank. Table 1 indicates the types of measuring devices applicable to wastewater treatment systems. The table indicates the primary measurement and type of device, some examples, general comments, capacities, and range. The open channel type are the flume and weir. Pressure pipeline flow type are differential producers, venturi tube, orifice plate, or flow nozzles. displacement meters, target meters, and velocity meters, propeller type. This slide is a continuation of Table 1, the types of measuring devices applicable to wastewater treatment systems. The primary measurement devices on this table are the magnetic meter, sonic or ultrasonic meter, vortex shedding meter, variable area rotimeter, open flow nozzles, level, staff gauge, float, capacitance probes, radio frequency probes, sonic or ultrasonic meters, differential pressure, and bubble tube. This slide is a continuation also of Table 1, the types of measuring devices applicable to wastewater treatment systems. Pressure, temperature sensors, analytical instruments, sand expansion, weight. This slide is again a continuation of Table 1, the types of measuring devices applicable to the wastewater treatment systems, gas concentration, time, revolution counters, power, electric power. Table 2 indicates the metering, instrumentation, and control requirements for industrial wastewater treatment systems. Indicated are the location and use, the type of measurement, type of instrument readout, range of measurement and readout, and then the controls, the item regulated, and the type of control. This slide is a continuation of Table 2, the metering, instrumentation, and control requirements for industrial wastewater treatment systems. Controller devices are needed to regulate the functions of equipment throughout the process. Controls may be classified by the degree of automation. With regard to the manual controls, use this type of control where the operator will start, stop, or adjust rates of operations based on instrument observations, laboratory tests, or indicated conditions. Automatic controls use this type to automatically start, stop, or regulate rates of operations in response to changes in a measured variable or other input. All equipment must also have manual control to override automatic control regardless of the degree of automation provided. Certain design considerations: many controls combine manual and automatic operations. The operator may initiate an automatic timed cycle backwash system or adjust set points of a proportional controller based on instrument observation. Controls that seldom require adjustment, such as rate of flow to filters, for example, should be manual. Controls requiring frequent adjustments, such as starting sump pumps, proportional chemical feeding, should be automatic. Whether the automation is on-off time cycle or proportional must be based on analysis of plant requirements. Now, some comments on chemical handling and feeding. See Table 3 for function of chemicals used for cyanide, oil, and metal removals. See Table 4 for the usual chemical strengths and other data on chemicals. Comments on the chemical handling and feeding. First, the handling. See Table 5 for handling precautions and provide the following: roofed unloading platforms, mechanical handling aids for unloading and transporting chemicals to the storage area, feed hoppers and solution tanks, dust control equipment for dry, dusty chemicals, wash down and clean up facilities for dry and liquid chemical spills. Table 3 indicates the function of chemicals for industrial and oily wastewater treatment. The chemicals, of course, are indicated in this table in the first column to the left. Then the comments on cyanide removal, metal removal, and oil removal in the ensuing columns. Table 4 indicates the data on chemicals for wastewater treatment. The chemical is indicated in the first column on the left, the forms in which it is available, shipping containers, bulk weight, commercial strength, water solubility, feeding form, feeder type, accessory equipment, suitable handling materials, and any additional comments. This slide is a continuation of Table 4, the data on chemicals for wastewater treatment. And this table is also a continuation of Table 4, the data on chemicals for wastewater treatment. And this slide is a continuation of Table 4, the data on the chemicals used for wastewater treatment. And a continuation of Table 4 is on this slide. And this is the concluding slide for Table 4. And as you can see, there are clearly many different chemicals that are used for different purposes in treating the wastewater. With regard to storage of chemicals, see Table 6 for space criteria and Table 7 for type criteria. Refer to ACI, Concrete Sanitary Engineering Structures, for criteria on protection of concrete against chemicals. Store materials in original containers in dry rooms on boards or pallets. Locate storage for dry chemicals at the level of feed hopper inlets if possible. Do not exceed safe floor load limits. For liquefied gas cylinders, provide cool, dry, well-ventilated above-ground storage rooms for non-combustible construction, remote from heat sources, walkways, elevators, stairways, and ventilating system intakes. Determine compatibility of all chemicals stored. Store incompatible chemicals separately, and observe proper personnel safety precautions. For on-site generation and feeding equipment such as ozone, ozone can be generated from air or from high-purity oxygen. Generation from air requires the air to be filtered and dried to a dew point less than minus 58 degrees Fahrenheit by desiccation and refrigeration. When using oxygen for the production of ozone, refrigeration and desiccation are not required except when recycling is used. Use oxygen for the generation of ozone where savings are indicated. Power consumption is halved when oxygen is used to generate ozone, but oxygen must be recycled or used for aeration to achieve overall economy. For ozone feeding equipment, use porous diffusers, injectors, or emulsion turbines to ensure optimum contact. Table 5, indicates chemical storage space criteria for different classes of chemicals and for non-interruptible and interruptible applications. Hypochlorite. Compare the cost of hypochlorite generated from brine with the cost of purchased hypochlorite solution delivered to the site. Generation is generally cheaper and may compare favorably with the cost of gaseous chlorine. Table 6 indicates chemical storage type criteria. The type of storage, handling requirements, safety and corrosion requirements. For chlorine dioxide can be generated using a solution of sodium chlorite and a solution feed-type gas chlorinator. Solutions are fed through packed media reactor for generation of chlorine dioxide in solution. Optimum operating conditions are pH less than 4, chlorine solution, 500 milligrams per liter, 1-to-1 weight ratio of pure chloride to chlorine, and reaction time greater than 1 minute. Reactor effluent will contain approximately 70% hypochlorite and 30% chlorine dioxide. Approximate yield is 0.4 pounds chlorine dioxide per pound of chlorine. Near 100% conversion to chlorine dioxide can be achieved by available recycle equipment. Yield is 1.0 pounds chlorine dioxide per pound of chlorine. Practical dosage rate of 6-to-1. System operating as flow proportional should provide acid injection directly upstream from the chlorinator injector to maintain optimum pH. Chlorine dioxide solutions are unstable in open vessels. Solution lines and diffusers must be designed so there is minimum possibility of chlorine dioxide coming out of solution. With regard to chemical feeders, see Table 7 for applications of various types of feeders. Dry feeder accessories. Dry feeders may require specific auxiliary equipment or accessories when the chemical to be fed has unusual characteristics. Accessories and the conditions under which they are used are as indicated in the table on this slide. The accessories are indicated in the first column: agitator, rotolock mechanism, dissolving chamber, dust collector, and vapor collector, and then the characteristics of the material requiring use of the accessory are indicated in the column on the right. Mechanisms of feeders must be constructed out of material resistant to substances to be handled. See Table 4 for guidance on materials selection. The accuracy of feeders should be in the ranges indicated here. Table 7 indicates the types of chemical feeders for wastewater treatment systems. The type of feeder, the use of the feeder, general comments, limitations and capacities, and then ranges. This slide is a continuation of Table 7, the types of chemical feeders for wastewater treatment systems. Gravimetric feeders are more expensive than volumetric feeders. Certain safety precautions to observe: provide the following safety factors as a minimum: first aid kit, continuous toxic gas monitors with alarms and pressure demand, self-contained breathing apparatus for emergency gas situations, a readily accessible potable water supply to wash away chemical spills, locate emergency shower and eye wash facilities where they are easily accessible to those in need, special handling clothing and accessories such as gloves, goggles, aprons, and dust masks, and adequate ventilation as determined by the appropriate industrial hygienist. No electrical convenience outlets in activated carbon storage or feeding rooms. Store activated carbon in a separate room with adequate fire protection. Entry into confined spaces will require adherence to a gas-free engineering program. With regard to the chemical feeder capacity and standby requirements, the base feeder capacity on maximum expected instantaneous flow and dosage. Essential non-interruptible chemical feeders such as disinfection units must have a standby unit having capacity equal to the largest unit. The need for standby units on other treatment processes depends on raw water quality and the specific treatment scheme. Where two chemical feed systems could use the same spare chemical feeder, one standby unit to serve both is adequate. Refer to EPA manual indicated for design criteria for mechanical, electrical, and fluid system component reliability. Document MCD 29. institutes sampling programs only as needed to obtain data for the design and operation of wastewater treatment facilities or to determine compliance with standards and the effect of waste streams, both raw and treated, on receiving waters. Refer to ASTM D3370 for a general discussion of sampling water and wastewater. With regard to sampling techniques, the collection point: collect all samples in conduits or channels at point where flow is highly turbulent. Collect sample from process tank only if tank contents are well mixed. Consider width, length, and depth when selecting sampling point from process tank. With regard to the type of sample, use samples composited on basis of time and flow, but take single grab samples when wastewater stream is intermittent or concentration is highly variable. When obtaining information for which time between collection and analysis of sample must be minimized, for example, sampling for dissolved oxygen, temperature, pH, chlorine demand, and residual chlorine. These cannot be composited. For ascertaining characteristics at extreme conditions, and samples for oil and grease may be manually composited. Automatic sampling is not normally accurate. The methods of sampling: use wide-mouthed containers to take grab samples. At small plants up to 1 million gallons per day, take composite samples manually by combining a series of regularly collected grab samples such that the contribution from a particular grab sample is proportional to the flow at the time it was taken. At large plants and industrial wastes, using automatic sampling devices that can be programmed for desired sampling method, that is, grab, continuous, or flow proportional composite. With regard to sample volume and preservation, the volume and preservation requirements depend on the analytical determinations to be carried out on the sample and the time between sample collection and analysis. See Table 8 for recommendations for sampling and sample preservation. Refer to American Public Health Association document Examination of Water and Wastewater, and to the EPA Manual of Methods for Chemical Analysis of Water and Wastes for specific recommendations regarding sample containers, volumes, and methods of sample preservation for each analytical measurement. The analytical methods to be employed: analytical methods available for quantitative determination of physical, biological, inorganic chemical, and organic chemical characteristics of wastewater samples are summarized in Table 9. Refer to APHA document Examination of Water and Wastewater for detailed laboratory procedures. For routine testing during plant operation, a routine sampling and analysis program to maintain plant operability and performance is required. This program is unique to the individual industrial and oily wastewater treatment facilities, and a general program cannot be developed in this discussion. The program should be fully developed in the Operations and Maintenance Manual for the facility and revised accordingly after plant startup and the 30-day performance certification period. The program should include the following: sample locations and methods, sample type, grab or composite, sampling frequency, and analyses required per sample. The Operations Manual should also identify minimum reporting requirements for regulatory compliance and should provide operating log sheets for recording operating data. Table 8 indicates recommendations for sample collections and preservation according to measurement. The type of measurement indicated on the first column on the left, followed by volume, container, preservative, and holding time. This slide is a continuation of Table 8, the recommendations for sample collection and preservation according to measurement. And this table this slide provides notes to Table 8. Table 9 indicates analytical methods for chemical handling and feeding, characteristics in the column on the left, followed by the method of analytic determination. And that brings us to the conclusion of this brief discussion of chemical feeding and controls for wastewater treatment plants. I hope it has been of some use to you and was about what you were looking for, and will be helpful to you on projects that come across your desk from time to time in the future. And with that, let me thank you again for letting me chat with you, and have a nice rest of the day.